one to come inside the can and the water.
Yeah.
All right, so there's our question. Give a circumstance where you have a negative acceleration, but you're not slowing down. What do you think? Keegan.
Tomazo.
What?
Tomazo.
Thomas.
It means you're going toward the object.
Anybody else want to answer this one without Thomas? Yes.
So you're in a pool and the waves are crashing you back. Do you keep wanting to go forward?
Sure.
You can't?
Oh, that's an example, yeah. So if you're going backwards, that's the negative direction. So if you're speeding up in the negative direction, that's the real answer to this one. So yeah, write down speeding up in the negative direction for the purpose of the final.
Backpedaling, right?
Yeah.
Backpedaling.
Yeah, if you're picking up speed going towards the origin, that would be an example of this.
Why don't we just call it an acceleration for negative acceleration?
Because negative acceleration does... Yeah, that's a good question. We'll have to try and coin that word. A couple examples from last hour that were real good. They said going down a hill, because you generally think of being down as negative. So if you're picking up speed going down, that would be an example of this too. I'll leave this up if you're still writing the question down. Worksheet number 2. What questions do you have? What would you like to talk about? We should do at least one from the first and the second side. Okay, 7 on the back. What on the front? 4. All right, 4 and 7. So number 4 on the front, we just got to create our velocity time graph. And it says the object moves away from the origin at a constant speed for 10 seconds, then it reverses and moves back toward the origin. So remind me which of those two things is positive. Is it going toward the origin or away?
It's going away from the origin.
Yeah. So when you're moving away from the origin, that's the positive direction. That would be a positive velocity. So we're starting by moving away from the origin. So that means we're going to start with a positive velocity. And it's a constant speed, so the velocity isn't changing. It's a horizontal line here. Then it says for the last 10 seconds, it reverses direction, moves back toward the origin at that same speed. So now we're going towards the origin. That is a negative velocity, which means it's got to be down here somewhere. And that would be your velocity time graph for number 4. All your lines on the front page and the back page should be horizontal because we have constant velocities for this whole worksheet. So let's take a look at the back side, number 7. Oh, that's a funky position time graph. So we've got 2 pieces of motion here. What can we figure out from a position time graph? What does that tell us about velocity? Keegan?
The slope.
The slope, absolutely. If you can find the slope of a position time graph, you automatically know what your velocity is. Ergo, that's where we have to go. So in number 7, you can see from 0 to 2 seconds, we've got a certain slope here. What slope is that from 0 to 2? Yep. Because rise over run is your slope, and that's equal to 1. So that means on our velocity time graph, we're going to start for those first 2 seconds with a velocity of positive 1. So these are the first 2 seconds. Now we got to find out the second part of that slope. What's that? Yes?
It's just negative half.
Not quite. You just got to reverse those two. Yeah, negative 2. Because it's rise over run, so we're going down 4, and we're going across 2. So down 4 would be like negative 4. So negative 4 over 2 is negative 2. So our slope is negative 2, and so therefore our velocity is going to be negative 2 for the last 2 seconds of this graph. Horizontal lines all around. Other questions on the worksheet you'd like to talk about? Wonderful. I'll come get those. Thank you. I miss anybody? So before we jump into some new stuff, really short amount of new stuff, I want to do a little bit of practice with these position and velocity time graphs, because ultimately where this section is going is being able to go between position time and velocity time easily. If you're given one of those two graphs, you should be able to draw the other one. So let's do 3 examples, and hopefully that should help you out a little bit. So we'll just be drawing 3 sets of those graphs there. Almost, yep.
Oh,
6.
So we'll just do 3 scenarios, put them on the graphs, and then I'll share with you an easier way to do that.
Why you just show us the easy way first?
Well, you actually kind of already know the easy way. Remember that this graph tells you velocity, right? So if you've got a positive slope, that means you're going to have a positive velocity. That's kind of the summary of this all. So let's just, for the sake of it, go through a couple examples. Here is example number 1. Now we're using Mr. Blue Shark here. And time begins right now. Time stops. So he begins at the origin, and he's at rest for a while. And then he starts to move with a constant speed away from it. So on our first position time graph, we're going to start at the origin, because he starts at the origin. As time goes on, he goes nowhere at the beginning. And then he starts to move away from the origin, which again is the positive direction. So that means we're going to be going up like this. As time goes on after this point, he's getting further and further away from x equals 0. He's getting further and further away from the origin. That's what's going on there. In terms of the velocity time graph, he begins with a velocity of 0 because he's holding still. And then he moves away from the origin, which again is the positive direction. So that would correspond to a constant positive velocity.
Holy moly, wow.
Everybody with me so far?
That's crazy.
All right. Let's do another scenario. Now he begins away from the origin. And time starts right now.
Just do a swimming motion.
Time stops.
He looked at you.
So, he started away from the origin, and he had a velocity at the very beginning, right from the get-go. And he was moving toward the origin with that velocity. So, would I begin my position time graph here?
No.
No, because he doesn't start at the origin.
At the end.
Yeah, he starts away from it a certain distance. So maybe it would begin up here. As time goes on, at the very beginning, he's going to get closer and closer to the origin because he started moving right away. Eventually, he reaches the origin. After that time, he holds still for the rest of the time.
And stares at us.
Yeah, eerily. So that would be our position time graph. In terms of velocity, he starts moving towards the origin, which is a negative velocity, which means we have a negative horizontal line for the velocity time graph. Yep. And then we go up to the 0 point because he has no velocity after he's at rest. So those would be the first two. The third one is a little different. Time begins right now.
Oh! Whoa!
Okay, and
He got
time
scared,
stopped. He did. He got scared.
Of you, because he was going toward me.
No one's allowed to make fun of Keegan's looks. So, when we're talking about position time graph, we got to think about what's happening here. So, there were two phases to this motion. That's four. Two phases to this motion. So, at the start, he was moving away from the origin with a certain speed, and then he moved back toward the origin after that. Did those speeds look about the same, or were they different? Yeah, a little bit different. So he started moving away with a certain speed, and that speed was a little bit slower compared to the second one. So when I'm going to draw this on a position versus time graph, the slope might be something like this. Kind of medium. And yeah. Very steep after that. He sees, something ugly over here. And then he... it was a what? A bigger shark. And then he turns back around and heads the other way to safety. So instead of this line coming down at the same slope, it's going to be steeper. Because the steeper the slope, the faster you're going. In terms of the velocity time graph, he starts by going away from the origin, so that's positive. And then he reverses direction, going toward the origin, which is negative. And it's going to be a larger value if we're looking at it there compared with the positive one.
That's crazy.
Would it ever go back that way?
No, that would mean going back in time. Time's always going to go forward, at least for now, until we talk about relativity later. So here's the easy way you can do this, because maybe you're not given a scenario. Maybe you're just given these graphs. You can easily figure out your velocity time graphs just by this. All you got to do is look at the slope. The slope of this graph tells you about velocity. Slope is 0, velocity is 0. Positive slope, positive velocity. Negative slope, negative velocity. Slope of 0, velocity of 0. Positive slope, positive velocity, negative slope, negative velocity. You get the idea. So you just got to look at the slopes. That's the easiest way to do these graphs. Questions?
No, sir.
Wonderful. As far as the new stuff goes today, I'm actually going to hand you out the notes.
Take the notes away?
Nope.
Sweet. It calls mosquito. Do we have to write anything on this?
No. I mean, you can if you want to.
Do we have homework?
Yes.
Is it easy again?
Should be. So last time, over the last 2 days, I was talking a little bit about the difference between speed and velocity. And there's really two differences. One of the differences is the fact that speed is never going to be negative. It's always going to be a positive value. Velocity can be negative because we're taking direction into account. The other difference, again, is that speed they're both calculated by doing change in distance over change in time, but that distance is different for each of these. For speed, this would be the addition of all of the distance that you've traveled, your entire path. Whether you went, all the way around the world and ended up in the same spot or not, it would be that entire distance. Velocity, though, this would just be the change in the distance from the spot you started to the spot you ended. So if you go all the way around the world and you end in the same spot you began, this value would be 0. So that's kind of what's being pointed out on this sheet here. And you can see that for average speed, I'm just adding up the absolute value of your changes in distance here. So change in distance 1 plus change in distance 2, even if you're going backwards and you have a negative change in distance, the absolute value fixes that, of course. So you're never going to have a negative number for your change in distance when you're dealing with speed. Add all that up, and you divide by time, and you get your average total speed. Average velocity, again, change in distance over change in time. You could think of this as your displacement from the 0 point divided by the total time. And just to make sure we're all clear on all this, I want to go through an example using that little graph. And that'll pretty much be the end of this, and you can start working on the homework. So here's the graph for actually, probably easier for the folks at home just to see the piece of paper. Yeah, so there's your graph. If you're watching this at home, pause it, maybe jot this down so you can take note of it. We're going to be calculating the average speed and the average velocity based on the information in that graph. So, just by looking at it here then, if I want to calculate the average speed, I got to add up all of the different distances here. So, from 0 to 3 seconds, we go 6 meters. So that's why 6 meters is in the first absolute value sign. And then we don't go anywhere, which is why 0 meters is in the next one. Then we go from 6 to 2, so that's like -4. So -4 is inside the absolute value sign there. And then after that, we've got a displacement or a distance of 0, because we don't go anywhere. And then from 10 to 11 seconds, we go from 2 to 4 to 6 meters. So that means your total distance traveled is 4. So when you add up all those absolute values, divide it by the total time of 11, you get your average speed, which is 1.27 meters per second. Questions on that? Average velocity is much easier, and that's nice because velocity is something we deal with a lot more often than speed. So in terms of the velocity here, all you're doing is taking your final position, which is 6, and your original position, that's 0. The difference between those two things, final 6 minus 0, that's 6, divided by the total time, which is 11, and you get your average velocity, which of course is going to be smaller, 0.545, because now we're taking this negative stuff into account. And that's how you get your average velocity. Questions? Wonderful. The very last thing I just want to mention is on these pieces of homework, going forward, you'll see references to motion maps. And I used to teach those, but I really wanted to shorten how long this chapter is, because it's one of the longer ones. And motion maps just ended up getting the axe, because they're only present really here. We don't use them in any other section. So I just want to introduce you to them, and then you can ignore any time it asks for a motion map on the homework. Basically, motion maps are using arrows and arrow lengths to show you what's going on with the motion. So let's say I have something that looks like this. This would mean that I've got an object that's moving with a pretty good speed. These arrow lengths represent how fast it's going. So if my next arrow would look something like this, and then something like this, what's happening?
Slowing down.
It's slowing down. If we see a dot with no arrow, what do you suppose has happened? It's stopped. Now, if it changes direction, we would go up, and then we would put an arrow in the opposite direction. So now, of course, you can tell it's picking up speed going back the other way. That's really all there is to motion maps. So if you want to do this on the homework, maybe you find some extra time or something, feel free to do that. No, but if you do it on the tests and if there's a quiz in this section, I'd probably give you some extra credit to that. But yeah, it's nothing more complicated than this. And that's all there is to it.